As you know, we will use the Laplace transformation to solve the differential equation. But if you notice that so far, right, we haven't learned anything about the differential equation and the relation with the Laplace transformation. There is nothing around we can use the Laplace for the derivatives or the differential equation. We just learned, right, how to take the Laplace of some elementary functions, and then we show the Laplace exist in for the functions when my function is piecewise continuous and if it satisfies the exponential order alpha. In this session, we are going to learn a couple more features, and then we are going to ask this question, right? What is the Laplace of y prime, right? Since if you want to solve the differential equation using the Laplace transformation, first of all, you need to be able to answer this question. Since when you are given the differential equation, you need to take the Laplace of the either sides. On the left hand side, you are going to have the differential equation, and then on the right hand side, you are going to have the functions. This is why in this session, okay, we are going to ask this question, but before that, I have another feature for you. So look at that. I can give you this theorem about multiplying the function, okay, by the exponential function. And there is an easy way, okay, to take the Laplace of that type of function. Look at it. If the Laplace transform of f, as you know, we denote in this way, ft, and then f of s, right? If you take the Laplace of the f, you're going to find out an s function we just did before, right? And then we created our table, guys. So, and then this is the notation I want you to get used to using it. Look at that. When you take the Laplace of f, I can use this notation as well, since later, okay, we're going to need to use this instead of L f of t. And what it says, I know this Laplace exists for s bigger than alpha. Then Laplace of e to the at times my function, look at it, right? I know what the Laplace of my f function, which is big F of s, but if I multiply my function by e to the at, that's all you need to do, guys. You just need to shift your Laplace transformation by a. It is so nice and it is so simple features. And I'm going to be using, okay, this, okay, with in some examples to learn, okay, how to use it. Basically, this is the right extra function here I have, and I'm multiplying by f, right, to get the Laplace of this new function. Okay. Let's see in an example. Laplace of e to the 3t times cosine 4t. Look at the function, right? I'm asking the Laplace of it. I have an exponential function here, and then I have an original function. What the theorem says, do you know the Laplace of the original function? Do I know? Yes, I know, right? From the table, the Laplace of cosine 4t is equal s over s squared plus 16. I can use my table, right, to get the Laplace of cosine 4t, guys. But my problem is not the Laplace of cosine 4t. My problem is about e to the 3t cosine 4t. When I have the right e to the 3t, look at that. This is equal to what? F of s, since my function is here f of t. So Laplace of f is equal f of s. But the Laplace of e to the 3t times my f function, cosine 4t, which is my f function, right, is going to be equal from the theorem. Look at that. I need to shift my big F. So my big F was equal s over s squared plus 16. If I shift by the number, what number? The number right on the top of e function. You see, this is my number I need to use, right, to shift my function. So a is equal to 3 here, and this is my number, which is b, which is equal 4. So this is why, look at, I'm gonna shift this one by a. How am I gonna shift it? Right? S minus that number. Let me use a different color for this one. S minus a, which is 3, guys, right? S minus a. And then also look at that, S minus 3. And then that's my shifting part. And also I'm gonna complete this with the rest. Still I have the 16 here. This is equal, look at that, the shifted version of my big S. That's how I use this theorem to find out another Laplace transformation of the given function. Another example, e to the 2t times sine 5t. Please solve, okay, before I solve this problem before I solve. So you can pause the video and then you can solve this problem and then come back to see, okay, what I do. Here I have e to the 2t function, as you see, and then this is my f of t, guys. First of all, I need to ask this question, what is my, the Laplace transform? So the Laplace transform of sine 5t, from the table you can see that it is going to be equal 5 over s squared plus 25, as you know. But to be able to find the Laplace of this function, e to the 2t times sine 5t, and this is my f, and my number a, which is equal to, that's why I need to shift by 2. If I shift this function, 5 over s minus 2 squared plus 25, which is equal the shifted version of original big f of s. This is f of s minus 2 function. Another example, e to the 3t times t. Same process I'm going to apply. The Laplace of what? Function t. From the table, the Laplace of this function is equal n factorial, which is the power of t, which is 1 over s to the n plus 1 over s squared. So what I will do, I will shift this one by the number I have on the top of e to the 3t. So that's why I can write in this way, s minus 3 squared, since look at that, my number a here is equal 3, this is going to be equal my shifted version of my big O of s. So this is the feature, Sometimes we are going to need to use it, especially when you have the function on the right-hand side, which is similar to that one. Look at it, I saw that one. If you remember from the undetermined coefficient technique, we mostly had, these type of functions on the right-hand side. So that's why, this is going to be a nice feature we are going to be using. Okay, now we can get back to this question, guys, I asked at the beginning. The question was this one. So I can ask you as an example. What is the Laplace of, the y prime? Or if you assume y is equal f of t, of course I can use both notation. So far I just use f of t notation, but when we start solving the linear differential equation, we are going to use always the y notation. But let me keep, since you got used to using it in this way. Laplace of f of t prime, or we can basically ask Laplace of the f prime. So how am I gonna solve this problem as an example? So let's make a small title here. So Laplace transform of derivative So far we have learned a lot of features, but still I don't have any features, right, I can use to solve the f prime. The only thing, right, I can use, please try to guess it, just the definition, guys. 0 to the infinite, e to the negative st, f prime dt. I need to take care of this integral. How? So, do you remember the technique you learned in Calc 2? What technique would you use to take care of this integral? I can use the integration by parts, guys. So this part is going to be dv, and then this part is going to be u. So use integration by parts. So my u is equal e to the negative st. Du is going to be equal negative se to the negative st. If the dv part is equal f prime dt, your v is going to be equal f. So let me apply the integration by parts formula, which is u times v, e to the negative st times f, but don't forget to use the bounds, 0 to the infinite, minus, right, v times du. Under the same integral, v times du, which is negative s I have, so I can take this out, it is going to be positive s, so f times e to the negative st dt. Okay, great. When I look at, okay, what I got after the integration by parts, what do you see, guys? Now look at that. This part is the Laplace transformation of my f function. So can I write in this way, s times f of s, or you can prefer to write in the other notation, s times Laplace of f, right? This is the Laplace of f since it is given by this integral 0 to the infinite, f times e to the negative st dt. Okay, what about this part, guys? This part, still, right, I need to apply the limit when n goes infinite. So e to the negative stf, 0 to the n. If you remember, right, this type of limit, when n goes infinite, I can take care of this limit, but I have the f here. But since I know f is the exponential order alpha function for this theorem, of course I need to assume, right, f is exponential order alpha. So I can definitely say, right, this part will go 0. So look at that, guys. Limit when n goes infinite, e to the negative s times n, f of t, correct? Minus e to the negative s times 0 times f of t plus s f of s. And then I know this part will go 0, and then this part is going to be 1. I'll look at what I have here. So this is f0, by the way, right? f0, I have this result, s times f of s minus f of 0. I'm done with the Laplace of the f prime, guys, now. Did you see that? So now I can write my Laplace transformation of f prime in this way. S times Laplace of f minus f of 0. So we need to notice that, look at this, guys, to be able to find the Laplace of f prime, you need to be given, right, an initial value. So this is the initial value, guys, right? That's why it is important to know the initial value. And then you are going to be solving the initial value problem when you take the Laplace transformation of the differential equation. Another question after solving this one. So now, can I ask this one, guys? What is the Laplace of, right, the f second prime? After, right, solving the Laplace of f prime, I think I can find a way, right, to take the Laplace of f second prime. Please think about it a minute, okay, before starting learning this part. If I assume g is equal f prime, then look at g prime would be equal f second prime. So instead of taking the Laplace of f second prime, I can go in this way. And then do I know what is the Laplace of g prime from the previous part? Yes. This is equal, look at it, s g of s minus g0. Okay. From the assumption, I know g0 is equal f prime 0. And then also, what is gs? gs is equal, right? gs is equal Laplace of gs. So Laplace of gs is equal Laplace of f prime, which is equal s times f of s minus f0, correct? Okay, let me put everything back into the right, this part. So s times g of s is equal, look at that, s times f of s minus f of 0. And now minus g of 0 is equal f prime 0. So it is going to be equal s squared f of s minus s times f of 0 minus f prime 0. Did you see, guys? This is the Laplace of the second derivative. So it seems we're good, right? We are at the point we can use the Laplace, right, to find out the Laplace of the differential equation, and then we can start solving the differential equation using the Laplace. So in the next session, we are going to start using these features to take the Laplace and then see if I can use, right, the Laplace to solve the differential equation, guys.